Deep beneath the icy veils of Europa and Enceladus, vast underground oceans swirl in darkness and silence, harboring secrets that could redefine life itself. These hidden worlds are not just cold, remote waters. They are alive with the potential for strange, alien ecosystems lurking beneath the surface. Imagine exploring a submerged universe, where every ripple and current might carry signals from unknown worlds teeming with possibilities. As we dive into these icy depths, we confront the question, could life be thriving in oceans that are yet to be fully revealed? Join us on this journey to uncover the mysteries of these secret oceans, where science meets wonder and the universe keeps whispering its most captivating secrets. Unveiling the hidden oceans, a journey begins. Beneath the icy shells of Europa and Enceladus lie vast, concealed oceans that could harbor the building blocks of life. These liquid water worlds are often likened to submerged gardens, where warm, salty seas ripple beneath frozen exteriors, creating a cosmic underwater realm that remains largely unexplored. Europa's ocean, kept in a liquid state by gravitational flexing from Jupiter's immense pull, is estimated to be twice the volume of Earth's oceans. Meanwhile, Enceladus's subsurface sea is vented through icy plumes, which have surprised scientists with their richness in organic molecules and other potential ingredients for life. The intriguing possibility that these hidden seas might sustain microbial ecosystems has stirred human curiosity, fueling efforts to probe their depths with robotic explorers. In Europa's shimmering, icy crust, cracks and fissures suggest dynamic interactions between the surface and the ocean beneath. Tidal forces generate friction that heats the subsurface water, preventing it from freezing solid and creating a stirring, ever-changing environment. This process could establish a diverse chemical landscape, rich in minerals and energy sources necessary for life. Hydrothermal vents on the ocean floor might spew mineral-rich fluids into the water column, fueling complex ecosystems akin to Earth's deep-sea vents, where life thrives independently of sunlight. Such ecosystems could be isolated, yet thriving, clinging to the abyssal teeming shadows of this alien world's ocean. On Enceladus, the situation becomes even more spectacular. The moon's south pole features towering plumes of water vapor and ice particles jetting into space, directly revealing the presence of a subsurface ocean. These fountains of material contain complex organic molecules, some of which are precursors to the chemistry that might enable life. Unlike Europa, where the ocean is hidden beneath a thick ice sheet, Enceladus offers a rare, tangible glimpse into its hidden depths through these plumes, providing a natural sampling of its oceanic chemistry. The detection of molecular hydrogen and other energy sources in these plumes hints at ongoing hydrothermal activity, which could serve as an energy wellspring that sustains microbial life in this extraterrestrial ocean. The allure of these submerged worlds lies not just in their potential to host life, but also in the mysteries they conceal. They are cosmic blue shadows, beckoning explorers to dive into their depths and uncover secrets that might redefine our understanding of life's resilience. Exploring Europa and Enceladus is akin to diving into a dark, unexplored underwater canyon, each discovery offering a glimpse into an alien biosphere, hidden but teeming with possibilities. The challenge lies in developing tools capable of piercing the ice, capturing samples, and deciphering the complex chemistry taking place in these icy oceans, all while respecting the fragile worlds that could be our next great frontier in the search for life beyond Earth. Historical origins of oceanic hypotheses. In the early days of planetary exploration, scientists approached the icy moons with a mixture of curiosity and skepticism. The idea that oceans might lurk beneath thick crusts of ice was initially a speculative notion, more a shower of hypotheses than a firm scientific consensus. Early telescopic observations of Europa and Enceladus revealed only faint glimmers of their true nature. Yet these distant images stirred imaginations, hinting at secrets hidden deep beneath frozen surfaces. The hypothesis of subsurface oceans began to take shape as astronomers noted surface features, such as fractures, ridges, and chaotic terrains, that bore a striking resemblance to geological activity seen on Earth's oceanic crusts. These clues suggested that these moons could harbor vast, liquid water seas, floating in perpetual darkness, akin to underwater caverns that conceal mysteries beyond our current reach. As instrumentation advanced, especially with the advent of space probes and spectrometers, the ideas surrounding these hidden oceans gained momentum. Data from missions like Voyager, Galileo, and Cassini revealed plumes of water vapor and organic molecules ejecting from Enceladus and Europa, like underwater geysers punctuating an otherwise frozen landscape. These observations transformed the hypothesis from a mere possibility to a compelling scientific pursuit. The notion that beneath icy shells, swirling water masses might serve as cradles for some form of life. This idea wasn't just about water. It was about worlds feeding their chaotically swirling oceans with energy, nutrients, and chemical gradients, creating environments that might resemble the deep-sea vents on Earth where life thrives without sunlight. The history of these hypotheses is woven with the threads of analogical thinking, comparing planetary surfaces and geological processes to those on Earth. Researchers pondered whether the heat generated internally through tidal flexing could keep the oceans liquid, similar to the way geothermal activity sustains life around Earth's hydrothermal vents. This thinking emerged from studies of tidal interactions with parent planets, Jupiter for Europa, Saturn for Enceladus, that stretch and bend these moons, heating their interiors enough to prevent oceans from freezing solid. The idea that these internal oceans could be teeming with microbial life, hidden beneath kilometers of ice, transformed the hypothesis into a vibrant field of astrobiology, fueled by the possibility of discovering extraterrestrial ecosystems forged in salty, dark waters. Throughout decades, the concept of ocean worlds evolved from speculative dreaming to a robust scientific hypothesis grounded in physical principles and indirect evidence. The hypothesis continues to ripple outward, inspiring missions with more sophisticated sensors and drills designed to penetrate ice and sample ocean waters directly. These oceanic hypotheses have become vital to understanding not just the physical nature of Europa and Enceladus, but also their potential as cradles of life, floating silently beneath icy oceans. Warm, dark, and mysterious, like enigmatic underwater caves waiting to reveal their secrets. Evidence from surface geology and ice shells. The surfaces of Europa and Enceladus reveal a mosaic of icy landscapes that whisper secrets of ocean worlds beneath. Europa's crust is layered with a complex network of cracks, ridges, and chaos terrains, suggesting ongoing tectonic-style processes. Satellite imagery has captured regions where the ice appears to have broken apart and refrozen, hinting at the dynamic life of its frozen exterior. These surface features act like scars from an ancient, yet continuously evolving, underwater realm. Ridges often trace the edges of vast, icy plates that may have shifted and realigned, hinting at a subsurface ocean that gently pushes and pulls on the frozen shell above. In the case of Enceladus, the tiger-stripe fractures near the South Pole cut a stark contrast across the icy surface. These fissures are not just superficial cracks. They serve as pathways for geyser-like plumes that spew water vapor, ice particles, and organic compounds into space. The spectral signature of these plumes suggests they originate from a salty, subsurface ocean that communicates with the surface through these cracks. The texture and distribution of the surface ice, combined with the thermal anomalies detected by orbiting instruments, point to a liquid water ocean kept warm at the base of the ice shell by tidal flexing. Each crack and scar is essentially a window into a murky, salt-encrusted ocean hiding underneath. The ice shells themselves also exhibit intriguing features that deepen the mystery of these ocean worlds. Europa's icy crust appears to have regions where it thickens and thins, producing potential areas of upwelling and downwelling, analogous to underwater currents. These variations in thickness could allow chemical nutrients and energy sources to migrate between the surface and the foreign ocean below. On Enceladus, the warmth and fracturing suggest that convection within the ice sheet might facilitate exchange, allowing chemicals and possibly microbial life to migrate and evolve in environments separate from the surface. Such processes resemble thermal convection currents deep in Earth's ocean floors, but within a frozen shell. Analyzing these surface geology signatures and their characteristics offers tantalizing clues about the potential habitability of these distant oceans. The presence of organic molecules in Enceladus plumes, coupled with the fractured, ice-bound crusts of Europa, hints at environments where microbial life, if it ever arises, could find refuge. These icy surfaces act like a neural network of calluses and scars, each one telling a story of invisible currents, chemical exchanges, and ecosystems that might hover just beneath. In this way, the geology of Europa and Enceladus becomes not just a record of past geophysical activity, but an open portal to enigmatic oceanic worlds where the possibility of tiny, resilient life forms remains an alluring, uncharted mystery. Magnetic field anomalies in subsurface liquids. Beneath the icy crusts of Europa and Enceladus, unseen forces ripple through their shadowy depths, whispering tales of hidden worlds. Magnetic field anomalies act like subtle fingerprints, revealing the presence of vast, liquid interiors that shimmer beneath frozen facades. These anomalies are often detected through meticulous measurements of how the moon's magnetic fields fluctuate as they orbit their parent planets, Jupiter and Saturn, each environment acting as a giant magnetometer. When scientists observe irregularities or unexpected magnetic signals, they interpret those as clues pointing toward conductive layers, likely salty, mineral-rich brine oceans that slosh and swirl beneath the icy shell. The existence of these subsurface oceans is further corroborated by the way their magnetic signatures change over time, matching the moon's orbital dance. For Europa, the induced magnetic fields are especially telling. As Jupiter's magnetic field fluctuates due to its rotation and magnetosphere, the conductive ocean beneath Europa's ice responds like a vast, submerged mirror, creating faint distortions in the detected magnetic signals. This indicates a highly saline, liquid ocean capable of conducting electricity, a key ingredient in the potential for alien life. Enceladus, with its geyser activity and icy plumes shooting into space, displays similar magnetic perturbations, hinting at an underground brine sea that stretches out beneath its shell, possibly connected to a global liquid reservoir. What makes these magnetic stories so enthralling is their whisper of possibility. These hidden oceans are not static. They're dynamic, churning with thermal and chemical activity. The magnetic anomalies suggest that the liquids are not just stagnant pools, but active, vigorous environments, shaped by the tidal flexing caused by gravitational tug-of-wars. This stretching could generate enough heat to keep water in a liquid state, fostering conditions that, at least conceptually, resemble Earth's deep-sea vents, fountains of life amid the darkness. In Europa's case, this could mean hydrothermal vents lined with mineral-laden fluids, warming pockets of chemistry where life might flourish unseen, nourished by a continuous cycle of chemical exchange. Positioned in the vast cosmic ocean, these moons resemble submerged starships, silently navigating their planetary orbits, their true depths cloaked in mystery. Studying the subtle tremors and magnetic whispers, clues encoded in complex electromagnetic patterns, researchers attempt to map out these secret aquatic worlds. The magnetic field anomalies act as cosmic compasses, guiding explorers through the dark waters toward potential habitats teeming with microbial life or even more complex organisms. Each anomaly is like a ripple in an infinite pond, hinting at the unseen currents of life that might pulsate beneath frozen surfaces. The prospect of discovering such ecosystems is tantalizing, transforming these moons from cold, barren worlds into cosmic archipelagos, holding secrets of life's resilience deep within their submerged oceans. Implications of tidal flexing and heating. The gravitational pull from their parent planets causes these icy moons to stretch and knead their interiors in a ceaseless ballet of tidal flexing. This repetitive deformation generates significant heat deep beneath their icy crusts, forging a hidden energy source that might sustain complex chemistry or even microbial life far beneath the surface. On Europa, the immense gravitational tug from Jupiter causes its ice shell to flex and crack, creating a network of fractures that are continually widened and closed by these forces. Beneath that brittle shell lies a vast, salty ocean, a potential habitat kept warm by the relentless internal heating from tidal flexing. Similarly, Enceladus experiences intense gravitational squeezing from Saturn and neighboring moons, which not only fractures its icy surface, but also drives up thermal activity inside. These dynamic processes maintain liquid layers in environments that are otherwise frozen solid, turning what might seem like distant, frozen worlds into undersea volcanoes and hydrothermal vents concealed beneath mile-thick ice sheets. Such tidal heating acts as a cosmic simmer, maintaining a delicate balance. The ocean remains liquid longer than pure radiogenic heating could sustain alone. The flexing generates heat primarily through friction inside the moon's interior, as rocks and liquid move against each other in a kind of celestial churning. For Europa, the thin, cracked crust over an ocean of liquid water becomes a perfect substrate for potential hydrothermal activity, similar to Earth's deep-sea vents teeming with life. Microorganisms, if they develop in this environment, would thrive around mineral-rich vent systems, feeding on chemical energy rather than sunlight. Enceladus's famed geysers, shooting plumes of water vapor and organic compounds into space, are direct manifestations of sudden internal heating and pressure buildup. These eruptions are an underwater proxy, fountains of nutrients and potential life-supporting compounds escaping from the depths. The rhythmic flexing not only sustains internal warmth, but also shapes the landscape itself. Surface features like Europa's chaos terrains, jumbled ice blocks, likely result from the stresses caused by tidal movements. These fractured landscapes may serve as pathways, allowing surface materials to interact with the subsurface ocean. Such exchanges could carry organic molecules, nutrients, or even microbial life from the ocean into the frozen crust, increasing the chances of life emerging or surviving in pockets of the ice. On Enceladus, the presence of complex organic compounds within the ejected plumes hints at chemical processes happening deep below, facilitated by tidal flexing that stirs the internal ocean and maintains a chemically rich environment. In both worlds, the ocean's existence is bound to this cosmic dance of flexing and heating, creating a watery universe layered with mystery, teeming with uncharted potential for life that remains just beneath a thin, icy lid, waiting for discovery. Cryovolcanic activity as a clue. Beneath the icy, shimmering crusts of Europa and Enceladus, evidence of cryovolcanic activity offers a tantalizing glimpse into their hidden depths. Unlike terrestrial volcanoes that spew molten rock, cryovolcanoes eject a mixture of water, ammonia, and other volatile compounds, flowing like rivers of icy slush into their subsurface oceans. These eruptions suggest that heat and pressure are at work beneath the surface, creating pathways for the internal ocean to interact with the moon's exterior environment. Such processes can be seen as underwater volcanoes, bubbling and venting in a landscape completely concealed beneath kilometers of ice. Observations from spacecraft have detected plumes of water vapor and icy particles spewing from cracks and fissures on Europa and Enceladus. These jets, perhaps analogous to geysers, serve as windows into their underground oceans. When the data from the Cassini mission revealed towering plumes erupting from Enceladus's south pole, it was like uncovering a bubbling, submerged volcano on an alien seafloor. Similarly, Europa's surface is dotted with chaotic terrains and smooth plains that might be shaped by cryovolcanic reshaping, hinting that its ocean might be intermittently venting through cracks. These eruptions not only confirm the presence of liquid water beneath the icy shell, but also indicate active processes that could harbor life. The compositions of these plumes hold clues about the chemical soup that exists below the surface. The detection of organic molecules, salts, and silica particles within the vapor jets deepens the mystery about the potential habitability of these hidden oceans. If these cryovolcanoes are releasing material formed through interactions with rocky cores, then they could be transporting nutrients, energy sources, and other building blocks for life from the depths of these concealed aquatic worlds. The idea of a submarine ecosystem thriving in such a dark, icy environment becomes increasingly plausible as evidence of ongoing cryovolcanic activity accumulates. Studying cryovolcanic activity as a signature of subsurface oceans is like listening to the heartbeat of these distant moons. Every eruption hints at the delicate balance of heat, pressure, and chemical processes happening far beneath the crust, a silent symphony of underwater phenomena. These icy vents might serve as portals to worlds teeming with microbial life or complex organic chemistry, using heat and underground chemistry as their main energy sources. Musings about submerged habitats amid freezing darkness become less speculative with each new discovery, revealing a universe where life could quietly flourish in unseen, icy underground oceans. Chemical signatures and possibility of life. Beneath the icy crusts of Europa and Enceladus, vast oceans stretch unseen, cloaked in darkness, yet potentially rich with the chemical whispers of life. These hidden seas are thought to harbor a complex web of chemical interactions, driven by hydrothermal vents and ocean rock interactions that dissolve minerals into the waters below. On Europa, evidence suggests that salty brines containing magnesium, sodium, and potassium could serve as the chemical backbone for potential biochemistries. Enceladus's plumes, spewing water and organic compounds into space, reveal a milieu teeming with molecular signatures that hint at more than simple chemistry. These signatures, complex organic molecules, nitrogenous compounds, and even methane, act as signposts guiding scientists toward environments in which life could ignite in an ocean of liquid. Scientists look at these chemical signatures with a mixture of wonder and cautious optimism. Organic molecules, traditionally associated with life here on Earth, have been detected in the plumes of Enceladus. These include simple hydrocarbons, amino acids, and complex carbon chains, all suspended in the icy spray. Such molecules could form the foundational blocks necessary for life, or at least provide the primary ingredients for prebiotic chemistry. Meanwhile, the salts and minerals dissolved from rocky seafloors serve as catalysts, facilitating reactions that could produce amino acids or nucleic acid components, crucial for the formation of life. This chemical soup, constantly stirred by hydrothermal activity, resembles a primordial origin site, an aquatic cradle where life might slip quietly into existence. The possibility of biochemical processes in these concealed oceans hinges on interactions between chemical energy sources and the waters themselves. Hydrothermal vents at the ocean floors could act as an underwater geyser of energy, releasing hydrogen, methane, and other compounds that organisms could exploit as fuel. These chemical gradients, similar to those seen around deep-sea hydrothermal vents on Earth, where entire ecosystems thrive without sunlight, offer a tantalizing scenario. Could microbial life be floating on the seafloor or suspended within the dark waters, feeding on chemicals produced by geological activity? The detection of molecular hydrogen on Enceladus hints at ongoing hydrothermal reactions, making it an intriguing candidate for harboring life forms adapted to extreme, hidden environments. Both moons serve as cosmic laboratories, where the chemistry of their oceans holds secrets that could redefine our understanding of life's potential. Each molecule, each ion, is a signal streaming up through the icy shell to whisper possibilities, of unseen life forms that might dance beneath the frozen surface, sustained by the same chemical dances that have sustained life on Earth in the most extreme environments. The ongoing analysis of these chemical signatures, an ongoing liquid symphony, keeps fueling curiosity as scientists endeavor to uncover whether these ocean worlds are simply chemical marvels or if they could also be cradles of some form of life waiting quietly in the depths. Comparative analysis of Europa and Enceladus. Beneath the icy crusts of Europa and Enceladus lie vast, hidden oceans that act as watery depths where life could potentially thrive in environments vastly different from Earth's surfaces. Europa's ocean, believed to be sandwiched beneath a thick shell of ice, might contain more water than all of Earth's oceans combined. Its connection with the Moon's rocky mantle suggests a continuous exchange of nutrients and minerals, creating a dynamic environment akin to Earth's deep-sea hydrothermal vents, hotspots of energetic chemical reactions that support diverse ecosystems. The possibility of these vents existing on Europa fuels speculation that, if life exists here, it may rely on chemosynthesis, harnessing the energy from underwater volcanic activity rather than sunlight. Enceladus offers a different, yet equally fascinating picture. Its southern polar region features plumes of water vapor and icy particles erupting into space, revealing a subsurface ocean in direct contact with a rocky core. These plumes, rich in organic molecules and salts, suggest active hydrothermal processes on the seafloor, possibly driven by tidal heating in response to Saturn's gravitational pull. The presence of complex organic compounds in the ejecta makes Enceladus a tantalizing candidate for harboring microbial life. Its cryovolcanoes swirl with the promise of a self-sustaining chemical soup, a miniature planetary ocean bubbling with potential for life-supporting chemistry. Comparing these moons feels like analyzing two underwater worlds separated by different depths and currents. Europa's ocean is believed to be millions of years old, perhaps a stable, layered ocean that has been protected from surface radiation by thick ice, maintaining a more isolated but potentially habitable environment. Meanwhile, Enceladus's ocean seems more youthful, with active plumes constantly replenishing its icy crust and offering direct sampling opportunities. Both worlds are connected to their planet's magnetic environments. Europa within Jupiter's intense magnetic field and Enceladus orbiting within Saturn's magnetosphere. Yet their oceanic environments are shaped differently by their size, heating mechanisms, and geological activity. The exploration of these icy oceans stirs the imagination. Each moon a concealed garden of underground streams and thermal vents, where dark waters may conceal life, forms unlike any we've encountered. The hydrothermal landscape of Europa might resemble the deep-sea vents embedded in Earth's crust, but enclosed in a frozen shell, while Enceladus's open plumes resemble a constantly bubbling, icy geyser, spewing secrets to space. Pondering these hidden worlds sparks wonder about life's resilience, a universal trait that might flourish in environments once considered too extreme or alien. The silent, submerged depths of Europa and Enceladus beckon with mysteries waiting to be unveiled, inviting us to consider that even oceanic worlds locked beneath miles of ice could host their own thriving ecosystems. Probing the ice shells, remote sensing techniques. Beneath the shimmering layers of ice on Europa and Enceladus lies an unseen universe, a hidden ocean teeming with potential for life's most elusive forms. Scientists have turned to remote sensing as their delicate probe, utilizing the faint whispers of energy that escape these icy giants to reconstruct their submerged worlds. One of the most vital tools in this quest is spectrometry, analyzing the light and energy reflected or emitted by the surface ice. Variations in spectral signatures across different wavelengths reveal clues about the composition of the ice shells, highlighting regions rich in salts, organics, or other biorelevant molecules, effectively peeling back layers of mystery without direct contact. Radar imaging further deepens this submerged exploration. By bouncing radio waves off the ice shells and studying the return signals, researchers can deduce the thickness and structure of the crusts. For example, NASA's Cassini mission employed synthetic aperture radar to peek through Enceladus's bright, icy surface, uncovering the characteristic undulations and fractures that hint at a liquid ocean lying beneath. These subtle oscillations in radar echoes suggest the presence of a flexible ice shell, one that may harbor cracks, vents, and pathways that serve as conduits for oceanic material reaching the surface. Such features can be telltale signs of active exchange, perhaps even pathways for life-sustaining compounds to escape into the stellar void. Infrared sensors add another layer of insight. By tracking thermal emissions, scientists can identify hotspots, areas where heat flows more strongly through the icy crust. These hotspots often correlate with geyser activity, like the plumes ejected from Enceladus, and can reveal where subsurface water interfaces are closest to the surface. In practice, infrared satellites or airborne instruments can map temperature gradients across the moons, painting a detailed thermal mosaic. These temperature anomalies not only mark active regions, but also hint at the dynamics within the ice shells, a swirling, ever-shifting frozen sea that behaves like an underwater landscape, full of hidden currents and subterranean structures. All these remote sensing techniques combine to create an underwater metaphor of exploration. Instead of diving into the icy depths themselves, scientists are tuning into the echoing calls of the hidden ocean, listening for the faint shifts, whispers, and vibrations that reveal the secrets beneath. Each wavelength, each pulse, provide a new piece of the puzzle, hinting at possible niches where microbial life might cling to existence amid the cold. The delicate dance of light and energy echoes the rhythm of a silent, flooded universe awaiting discovery, a liquid core with the potential to harbor the earliest sparks of life in a universe that remains largely an underwater unknown. Subsurface ocean dynamics and circulation. Beneath the icy crusts of Europa and Enceladus, vast liquid oceans swirl and churn in silent, perpetual motion. These hidden water worlds are dynamic systems, where salinity gradients, temperature differences, and gravitational influences create complex circulation patterns. Unlike Earth's oceans, which are directly exposed to the atmosphere, these subsurface lakes are enclosed in a thick shell of ice, making their internal currents exceptionally mysterious. Yet, evidence suggests that their movements are not random, but intricately linked to tidal forces exerted by their parent planets, Jupiter and Saturn respectively. These gravitational tugs generate periodic flexing of the ice shells, inducing frictional heat and possibly driving convection currents deep within. This convection acts like a colossal, slow-moving engine, stirring the ocean's depths and creating pathways that might allow chemical nutrients and energy sources to circulate. Warm plumes may rise from the ocean floor, where hydrothermal vents spew mineral-rich fluids into the cold abyss. Such vents could establish localized circulation zones, similar to Earth's deep-sea vent systems, fostering environments that might sustain microbial life. These circulation patterns could also create regional temperature variations and chemical gradients that serve as guiding beacons for potential biological ecosystems. In Enceladus's case, the famous geyser plumes are likely connected to subsurface currents, transporting material from the ocean floor outward through fractures in the ice crust. The flow of these underground seas is not uniform, but characterized by swirling eddies and layered stratifications. Variations in salinity and temperature create density differences, which in turn organize the circulation into stratified layers. Descending colder, salter water might sink along certain pathways, while warmer, less salty water rises elsewhere, establishing a balanced yet continually shifting ballet of movement. Such layered flows could guide chemical nutrients to specific regions, similar to marine upwellings that nourish surface ecosystems on Earth. These processes may happen over spans of centuries or millennia, gradually redistributing energy and matter across the ocean's expanse. Ultimately, Understanding how these unseen seas circulate is like deciphering an underwater symphony conducted solely through gravitational forces and thermal variations. Each movement, each swirl of water, holds clues to the potential habitability of these alien worlds. Their hidden circulations could deliver life-sustaining chemicals to the ocean floor, fostering environments where simple organisms might exist in isolated pockets of perpetual darkness. The currents forge an unseen, ever-changing landscape, an oceanic ballet that conceals the secrets of what might still be alive beneath the icy horizons. Potential habitats in subsurface environments. Beneath the icy crusts of Europa and Enceladus lies a hidden world that resembles an expansive, silent ocean, a submerged realm where conditions could harbor the possibility of life. These subterranean oceans, kept warm and liquid by tidal flexing and radioactive decay, resemble vast underwater reservoirs waiting to be explored. The fascinating aspect is that these environments are shielded from the harsh vacuum of space, creating a pristine habitat where life might discover a haven far from the surface's extreme conditions. The potential for microhabitats in these vast alien seas hinges on the presence of energy sources and chemical ingredients necessary for life. Much like the hydrothermal vents on Earth's ocean floors, hidden pockets teeming with possibilities beneath even the deepest water layers. In these concealed depths, the interactions between water and the rocky mantles of their moons could generate chemically rich environments. The exchange of minerals from the moon's rocky core can lead to the formation of hydrothermal vents, chimneys of mineral deposits that spew superheated, mineral-laden water into the ocean. Here, in the dark, without sunlight, life might rely on chemosynthesis rather than photosynthesis, much like the organisms thriving near Earth's hydrothermal vents. These ecosystems could sustain microbes capable of utilizing hydrogen, sulfur compounds, or methane, which are believed to be present in trace amounts. These chemical energy pathways open a portal to understanding how life might endure in environments that are oceans equivalent of underwater volcanoes or geothermal springs. The complex chemistry occurring at the interface of ice and water, within tiny cracks and fissures in the ice shell, could also foster the formation of microhabitats. Subsurface lakes, or brine pockets, isolated enclaves of high salinity, may act as oases where microbial communities could find refuge. These pockets might be akin to Earth's extreme environments, halophiles and methanogens thriving in salty, anoxic conditions. The constant movement of hydrothermal fluids, combined with possible mineral deposits, could create chemical gradients, interfaces where life might concentrate and evolve. Such environments resemble underwater caves or mineral-rich hot springs on Earth, where life is often most diverse and resilient. All of these factors combine to form a universe of possibilities beneath Europa's icy shell or Enceladus's geyser-laden surface. The immense pressure, constant renewal of nutrients from hydrothermal activity, and the absence of sunlight do not necessarily limit habitability. Instead, they reshape our image of where life can flourish, inside cracks, at the edges of mineral deposits, or around chemically energized vents. As technology advances, exploring these potential habitats becomes more than wishful thinking. It is a bridge to understanding whether life within such submerged worlds is not only possible, but perhaps surprisingly common across our solar system's watery moons. Challenges in direct exploration. Beneath the glossy veneer of Europa and Enceladus's icy shells lie vast, hidden oceans that are as enigmatic as they are alluring. Yet, venturing directly into these watery depths presents a suite of formidable obstacles, akin to navigating a sunken labyrinth cloaked in perpetual darkness. One of the most immediate hurdles is penetrating the thick ice crust that shields these oceans from our reach. Europa's ice shell is estimated to be at least 15 to 25 kilometers thick, with some models suggesting even greater depths. On Enceladus, while the ice shell might be thinner, perhaps only a few kilometers at its thinnest points, the challenge remains daunting. Drilling or melting through such extensive ice requires equipment that can withstand extreme cold, intense pressure, and a relentless battering of radiation belts in Jupiter's magnetosphere. The environment beneath these icy covers isn't welcoming either. Once the probe breaches the surface, it confronts a chamber of darkness and pressure unlike any terrestrial ocean. The pressure at Europa's ocean floor could surpass 100 megapascals, crushing any unprepared craft trying to explore. The water is a labyrinth of potential chemical reactions and mineral interactions, ever-changing, unpredictable, and filled with unknown variables. Sending sensors or submersibles into this environment demands autonomous systems capable of not just survival, but meaningful exploration without real-time human intervention, as direct communication signals would take hours or even days to traverse the vast distance from Earth. The lag makes remote operation a challenge, forcing explorers to depend heavily on pre-programmed intelligence and adaptive AI capable of making split-second decisions in an alien, oceanic realm. Another core challenge involves the corrosive, chemically rich nature of these extraterrestrial oceans. Organic compounds, salts, and potentially even hydrothermal vent-like phenomena could be lurking beneath the ice, creating an environment that is hazardous for machinery. Winds of radiation bombard the icy shell, embedding the surface with energetic particles that can degrade electronics and sensors. Designing equipment that can operate reliably in such hostile conditions necessitates advancements in materials science and engineering, pushing current technology to its limits. This is further complicated by the difficulty of delivering power. Solar energy becomes practically useless at such distance from the sun, leaving options like nuclear or radioisotope power sources that must be both compact and highly durable. The final obstacle lies in the logistical and financial enormity of deploying a mission capable of overcoming these icy barriers. Every step toward the hidden ocean, drilling, melting, deploying, requires a massive investment in both technology and resources, with a high degree of risk. No matter how sophisticated our robots become, they remain dependent on precise engineering, resilience against undiscovered hazards, and future innovations that are yet to be conceived. The prospect of peering into these ancient, icy underwater worlds, teeming perhaps with microbial life or complex chemical ecosystems, compels a delicate balance of curiosity and caution. For all the scientific allure, the journey remains a venture into the unknown, a plunge into an ocean where dangers lurk beneath the surface like silent predators waiting in pitch darkness. Future missions and technological innovations. Beneath the icy veneer of Europa and Enceladus, humanity envisions a vast, hidden ocean teeming with possibilities. Future missions are now veering toward the frontiers of technological innovation, seeking to peer through thick ice sheets and unlock whispers of microbial life lurking in these dark, pressurized waters. Cutting-edge concepts like ice-penetrating probes and autonomous underwater explorers are being designed to navigate the treacherous terrain of frozen crusts, diving into the unknown depths with precision sensors and miniature laboratories on board. These innovations aim to act like underwater sonar, mapping fluid flows and detecting chemical signatures indicative of biological processes, all while withstanding extreme cold and radiation environments that are unlike anything found on Earth. One particularly exciting development involves the deployment of cryobot technologies, heat-powered drills equipped with sensors and robotic arms that can melt through miles of ice, creating pathways for submersible drones to explore. These robotic submarines might resemble tiny bathyscaphes, navigating the liquid ocean beneath with heightened autonomy, equipped with spectrometers, microscopes, and chemical analyzers. As they drift through the alien seas, they could scan for organic molecules, hydrothermal vent-like activity, or other signs of habitability. The challenge lies in designing these devices to endure intense pressure and darkness, while still possessing the agility and intelligence to seek out the faint traces of life that might be there, floating like unseen shadows in the depths. Innovations in remote sensing and satellite technology also hold promise, offering the potential to detect subtle clues from orbit, like faint thermal anomalies or surface disruptions, that suggest subsurface activity below the thick ice. Future missions could send sophisticated orbiter platforms capable of analyzing the surface and near-surface environment with high precision, using radar and infrared imaging to craft a three-dimensional map of the ice shell structure and dynamics. Sometimes it's rather poetic. These instruments act as telescopic ears and eyes tuned to whispers from beneath, revealing hidden oases of water, fissures, and plumes that act as geysers, ejected from the ocean below and providing a brief glimpse, a splash of evidence that life may be possible in these cold, silent worlds. Advancements in power sources and communication are equally critical, as they serve as the unseen currents guiding explorers through what is essentially an icy abyss. Compact nuclear reactors or radioisotope power sources might fuel these remote explorers, enabling long-term missions far from Earth's reach. Meanwhile, novel tethered systems or relay satellites could ferry data back to Earth in real time, overcoming signal delays and ensuring safe navigation through the opaque ice. As these innovations come together, they will forge a conduit for humankind's curiosity, an oceanic voyage of discovery into alien worlds that could redefine what we understand about life's tenacity and adaptability beyond Earth. The broader significance of discovering ocean worlds. Beneath the icy shells of Europa and Enceladus lie vast, concealed oceans, their depths holding secrets that could redefine our understanding of life itself. These hidden water worlds resemble submerged labyrinths, dark, cold, and uncharted, yet teeming with possibilities that excite both scientists and explorers alike. The presence of liquid water beneath thick layers of ice raises profound questions. Could these alien seas harbor life that is entirely different from anything on Earth? Hauntingly beautiful and mystifying, these worlds act like underwater caves on a planetary scale, where conditions might mimic the deep-sea vents and hydrothermal systems that support extremophiles here on our own planet. It's an extraordinary thought. Life thriving in alien pockets of energy and chemical gradients, far from sunlight, but sustained by underground warmth and chemical richness. Discovering these ocean worlds revolutionizes the way we think about where life might exist in the cosmos. It broadens the potential habitats far beyond familiar terrestrial environments, turning the universe into an expansive, submerged garden waiting to be explored. Unlike planets or moons that are barren, these oceans are essentially filled with the possibility of microbial communities, perhaps even more complex ecosystems that we haven't yet imagined. Think of these worlds as cosmic shipwrecks, silent and mysterious, where signs of life could be encoded in the mineral deposits, in the plumes of water vapor venting into space, or in the chemical signatures frozen beneath the icy crust. Understanding the chemistry and geology of these environments can provide clues about the resilience of life amid harsh conditions, feeding curiosity about life's boundaries and potential universality. The broader implications extend even beyond biology. These concealed oceans serve as natural laboratories, alien versions of Earth's deep-sea vents, where the physics and chemistry of extreme environments can be studied without the planetary surface interference. They are windows into planetary evolution, offering insight into how moons and planets might sustain or lose their internal heat over eons. As probes and telescopes peer beneath the surface ice, the possibility of detecting hydrothermal activity or organic molecules becomes increasingly tangible. This, in turn, sparks curiosity about how life might arise and sustain itself in such sequestered worlds, spaces where the familiar rules of terrestrial biology may be stretched into new, exotic forms. Ultimately, the discovery of ocean worlds underscores a humbling truth. Space isn't a barren void, but a complex terrarium of environments, some of which could be remarkably similar to Earth's hidden niches. These oceans act as celestial echoes, reminding us that life could be more resilient, adaptable, and widespread than we have ever dared to imagine. The search for life beneath the ice evokes an underwater adventure, a voyage into the deepest, most mysterious parts of our solar system's enclosed waters, where the ripple of a chemical reaction might signal the presence of an entirely new form of life. Their exploration invites us to reconsider our place in the universe, opening up a submerged frontier filled with potential and wonder. Beneath the icy shells of Europa and Enceladus lie vast, dark oceans that harbor some of the most intriguing prospects for extraterrestrial life. These hidden waters are thought to be towering, endless currents of salty, mineral-laden liquid water, a prolific environment for complex chemical interactions. The thickness of Europa's ice shell, believed to be several kilometers, conceals a global ocean beneath, kept in a liquid state by sheer heating and tidal flexing driven by Jupiter's gravitational tug. Meanwhile, Enceladus's subsurface ocean is exposed sporadically through plumes spewing water vapor, organic compounds, and salts into space, painting a dynamic picture of a watery world in flux. The possibility of life in these unseen depths hinges on the presence of essential ingredients: liquid water, organic molecules, and energy sources. On Earth, hydrothermal vents on the ocean floor spill out mineral-rich fluids that foster complex ecosystems relying on chemosynthesis rather than photosynthesis. If similar conditions exist at the base of Europa's ocean or within Enceladus's plumes, they could serve as underwater composters, fueling microbial communities that thrive entirely independent of sunlight. Chemosynthetic life might cluster around hydrothermal vents or mineral deposits deep beneath the icy surface, relying on chemical energy just as vent organisms do on Earth, in high-pressure environments where the light cannot reach. The challenge lies in the fact that these oceans are largely sealed from our direct view. Still, data collected from orbiters and flybys hints at a landscape ripe with potential. Europa's cracked ice crust exhibits a network of ridges, chaos terrains, and potential ocean floor interactions, all of which could nurture pockets of chemical richness. Enceladus's geyser-like eruptions reveal a surprising amount of organic molecules and salts, signatures that suggest a complex interplay of oceanic chemistry. These plumes offer a tantalizing glimpse of the ocean's composition, allowing scientists to analyze the unseen ecosystem without needing to drill through kilometers of ice. The chemistry within these frigid, dark waters might be the key to unlocking a hidden biosphere, a secret ocean teeming with microbial life that stubbornly clings to existence in its icy abyss. Understanding these aquatic worlds involves deciphering their mineral compositions, chemical gradients, and heat flow. Such factors create underwater terrains that could resemble Earth's deep-sea hydrothermal fields, hotspots where life may emerge or persist. The possibility that chemosynthetic organisms could be submarine explorers themselves, consuming chemical energy from mineral interactions, keeps the scientific curiosity alive. Future missions aim to penetrate the ice, analyze plume material directly, and perhaps even locate the telltale signs of biological activity. Each discovery would add a new chapter to the story of these secret oceans, transforming our notion of where life might exist and reminding us how vast, mysterious, and interconnected the universe's watery depths truly are. As we journey through the icy depths of Europa and Enceladus, we've glimpsed the whispers of hidden oceans swirling beneath frozen surfaces, worlds that might harbor life in ways we've only just begun to imagine. These secret aquatic realms, shrouded in mystery and wonder, serve as cosmic treasuries of possibility, inviting us to ponder what might dwell in their shadowy depths. It's easy to feel like explorers peering into an unfathomable abyss, where each ripple hints at stories unfolding far beneath our view. For now, these icy oceans remain enigmatic, but their potential to harbor life stirs an innate curiosity within us all, like uncharted waters calling out to be explored. If you're captivated by the idea that life could be quietly thriving in these celestial seas, stay tuned. We'll continue to navigate the depths of these fascinating worlds together. There's so much more on the horizon: new discoveries, innovative missions, and the ongoing quest to find our cosmic neighbors. So, keep your eyes open and your imagination primed. The universe's hidden oceans may very well hold answers to questions we haven't even dreamed of yet. Until then, the journey continues, and the mystery of Europa and Enceladus' secret worlds beckons us onward.